Yeah, thank you very much. So I appreciate very much for your introduction. Thank you very much. So it is my great pleasure to give a talk on our latest understanding on the binary neutron star mergers that is obtained by the numerical relativity simulations. So today I'll focus on the result on the numerical relativity, in particular for the binary neutron star merger. And this is the content of this talk. So first, I'd like to give a brief introduction of what is the binary neutron stars and how the binary neutron star is formed, and then how the binary neutron star merge eventually. And then I will summarize the current understanding of the binary neutron star mergers obtained by numerical relativity simulation. And then I'll describe the characteristic of gravitational waves from the binary neutron star merger, and also the relation between the gravitational waves form and the equation of state of neutron star. And then I will change the subject, and I talk about the mass ejection. So recently, this community has found that after the merger, a large amount of mass is ejected from the system. So ejected means that matter gets escape velocity from the system. And then it has been suggested that such a ejecta could shine and could be an electromagnetic counterparts of the gravitational wave signal. This is also found by recent numerical relativity simulation, and I'd like to tell you that what is found and so on and so on. And finally, I'll tell you the implication of the kilonova associated with short gamma ray bursts, which was discovered last year. Okay, so first of all, let me start with a brief introduction about how the binary neutron stars are formed. So this is a typical scenario for the formation of binary neutron stars. So for example, Chris Belczynski often wrote a paper about these topics. And for typical case, binary neutron stars are formed as a result of the evolution of two massive star binaries. So here, massive star binary means that we have two massive stars, with mass larger than 10 solar mass. So let A star be the massive star and B is a smaller star. So in this case, massive star evolves earlier and eventually explode and to be a neutron star and to occur the supernova explosion. And for this case, A star evolve, and then it becomes usually giant. Then this is a common envelope phase. Common envelope phase is formed, and orbital separation slightly change due to the effect by the common envelope phase. But anyway, for this case, nothing happens between the merger, nothing special happens between the binary, and then neutron star plus massive star system will be formed. Then star B evolve, and again, this becomes a giant, and then this phase become very critical for forming the binary neutron stars according to the typical scenario by Belczynski and Vicky Cargera and so on and so on. So for this phase, what happens is that neutron star, the orbit of neutron star shrink due to the common envelope phase. And if common envelope phase is too dense, neutron star would merge to be this core of the massive star. Then binary neutron star will not be able to be formed. On the other hand, if the orbital separation is too large, and in this case, after the supernova explosion, usually we believe that neutron star has a kick velocity. Then if the orbital separation is too huge, and this means that the orbital velocity is smaller than the kick velocity, binary is likely to be disrupted. So this means that fine-tuning is necessary to make a binary neutron star. And then in a very lucky case, according to the scenario, binary neutron star will be formed, and this will be an interesting system to be observed. So And then, so after the formation of binary neutron stars, it will evolve simply due to the emission of gravitational wave, because this is a very clean system. And then, so it will eventually merge. So, but after the long-term evolution of the system due to the emission of gravitational waves, so long-term means that typically about 100 million years, something like that. Then, so it eventually merge and to be some major object. And so subject in this talk is just here. Okay, so in the first page, so I talked about the typical merger scenario, but this formation scenario is supported by the latest observation for the binary neutron stars. This is the 6 compact binary neutron stars observed by radio observation. But this is found. This is found in globular cluster, but the others are found in a field. So this means that for this case, so binary neutron star may be formed as a result of the 3-body encounter. But for other cases, so we may believe that formation. So these are formed as a result of the evolution of massive binary stars. So and anyway, so this is evidence that the typical scenario is likely to be correct. And according to this observation, we could estimate the merger rate. So I should write that so names of Starfini. So he did so very pioneering work of this merger rate. But anyway, so this last line shows that lifetime of this binary system in unit of the 100 million years. And this shows that for these binaries, lifetime is much shorter than the Hubble time, so age of the universe. So this means that this suggests that there are many binary neutron stars that will merge within the Hubble time. And according to the statistical study by these people, the galactic merger rate is this value, so 1 every about 10,000 years, or 1 every million years, something like that. So it's so error is very large. But extrapolating this value to the cosmological distance, merger rate in our universe become about 1 to 100 every year in a distance within a distance of 300 megaparsecs. This means that even for the worst case, so 1 every per year within a distance of 300 megaparsecs a cube may be expected, and so this means that this suggests that binary neutron star is a promising source of gravitational waves. Okay, so let me summarize that why the binary neutron star merger is important. So I think that there are at least 5 motivations for studying the binary neutron star merger. One is that, as already said, that this is most promising sources of gravitational waves for advanced detectors such as advanced LIGO and Berg and Kagura. Sorry, so because I am Japanese, I show the Kagura here. So usually we should write LIGO here, but because I'm Japanese, I show Kagura here. And the second motivation comes from the fact that so binary neutron star is a merger binary neutron star is in a sense a huge collider of nuclear matter. So this means that it's an invariable laboratory for studying high density nuclear matter. So this is the second motivation. And the third motivation is that comes from the fact that merger binary neutron star has been suggested that it's a promising source of the short gamma ray burst. And fourth and fifth rather new. So fourth motivation comes from is that as I already said that so after the merger, so huge amount of ejecta may be expected. So and ejecta could shine and emit electromagnetic signals. So this become now a very important subject. And the fifth one is that related with heavy elements. So binary neutron star merger anyway ejects some material, And such material could be origin of the so-called rapid process heavy elements. So now, so we observe along, for example, solar system. We have R process heavy elements, but we don't know that exactly that what is the origin of such heavy element. And binary merger and ejecta from the binary neutron star could be promising sources of R process heavy elements, and this also give us stimulate us to study the binary neutron star merger. But so today, so I don't have enough time, so I'll focus on this topic, so gravitational waves and equation state, and also I'll talk about the electromagnetic counterparts. So I will talk on the ejecta and electromagnetic signal from the binary neutron star merger. Okay, so next, so I would like to talk on the our current understanding of the binary neutron star merger, so based on the latest numerical relativity studies. So anyway, so nice thing is now is that so numerical relativity can answer what happens in the merger of binary neutron stars. It was not possible 10 years ago, but now it's possible. So, but anyway, so about 10 years ago, so we could do, but so we never expect that we are able to do a very scientific simulation now. So, but now, so it's possible to perform a scientific simulation for binary neutron star merger. But for scientific run, so we have to be very careful in preparing the initial condition, and also we need a systematic study. Okay, so what is necessary in the scientific initial condition? So anyway, so we have many huge amount of parameter space in this problem. So mass and spin and the equation of state and so on, so on. But so observation helps that restricting the parameter space. For example, so according to the binary pulse observation, mass of the binary neutron star is likely to be in a very narrow range between this range. So let me show you a table again. This is a list of the 6 binary neutron stars, and this is a mass for each mass. So this is a 1.44, and this is a 1.389, and so on, so on. And you can see that mass is in a very narrow range for this binary. So if we believe that this is a typical value of binary neutron stars, we may restrict performing a simulation in this range. And also, a spin is likely, so according to the observation of binary neutron stars, so spin is likely to be negligible or small. And again, this is a table, and this shows a typical magnetic field of the probably fast formed neutron stars. For this case, only for this case, neutron star is a second born one, but probably so for the other cases, so I mean that for the if the magnetic field is relatively small, so typically so magnetic field of a neutron star is 10 to 12 or something like that, gas. But so for this smaller case, so we usually believe that it is formed at the first burst. And for this fast neutron stars, typical rotation spin velocity is about 10th of a millisecond. So this means that it's much smaller than the maximum, possible maximum. Possible maximum is about half millisecond or something like that. So compared with the half millisecond, this is much longer. So this means that the spin is not very large. And in addition to this data, so we can estimate that the magnetic dipole radiation time scale. This is a magnetic dipole radiation time scale, so it is evaluated from this value and this value, and in unit of the 100 million years. And this is a lifetime of a binary. So you can see that for most of them, magnetic radiation time scale is shorter than the lifetime of the binary. So this means that at the merger, so spin is negligible for this binary. Exception is that for this double pulsar, the so-called double pulsar, for double pulsar, so magnetic dipole radiation time scale is about twice as long as the emission time scale of gravitational waves. But still, this is not extremely large, so it may not be negligible, but it's still small. So this means that we may believe that the spin of a binary neutron star is not very large, and we may focus only on the small spin case. But by contrast to the mass and spin, so we don't know the equation state of neutron star. So this means that for these initial condition is fairly well defined. But for this, so we have to take into account a wide variety. Okay. So this is information about equation state. This shows that the mass as a function of the radius of a single spherical neutron star, and each curve shows a relation of mass and radius for a given equation state. And you see that there are many curves, so this means that there are many theoretical curves of theoretical equation state. And so latest discovery of two solar mass neutron stars, this one, constrain significantly the possible equation state. For example, these guys cannot explain the two solar mass, so this should be rejected. But still, there are many equation states that which two solar mass neutron stars can explain. And in addition to this neutron stars, recent X-ray observations suggest that the radius of a neutron star is likely to be in this range. This is not very tight, but it is a good suggestion. But still, there are many candidates like this. So this means that we have to perform a systematic study for numerical-relativity simulation. So anyway, this is a conclusion here. Many simulations with many equation states are needed for a systematic study, although the mass and spin are being in a very narrow range. Okay, so anyway, so we have been working in such a simulation, so changing the mass in a narrow range and neglecting spin, but taking into account the many equation state. And but anyway, so we found that very interesting things. So before showing our results, so I'll summarize that expected fate. After the merger of binary neutron stars, we have two possibilities. One is that black hole is formed soon, because each neutron star has a 1.35 solar mass. Total mass will be 2.7 or 2.6, so it is huge. So black hole may be formed soon after the merger. The other possibility is that massive neutron star is formed. So this could be also possible if equation of state is stiff, or rapid rotation after the merger. So merged object has a huge amount of angular momentum, and then so centrifugal force could support the massive neutron star. So anyway, so we have two possibilities, and the fate, of course, could depend strongly on the total mass and the equation of state. But the latest observation considering that the total mass is not very large, so between 2.6 and 2.8. And also, a recent discovery of two solar mass neutron stars constrains the equation of state. So equation state should be fairly stiff. So to explain this constraint. So as a result, so numerical relativity simulation discovered that fate 2 is a case for a typical case. Okay, from now, so I'm going to show you an animation for a merger of a binary neutron star with this mass, so equal mass binary neutron star with each mass 1.35 solar mass. So I will show you 4 animations. So for this one, so radius is rather small, 11 kilometer. This one is about 12.5 kilometer, and 13.5 kilometer, and 40.5 kilometer. So okay, so let's show you animation. This is a density contour in the orbital plane. It takes a little bit time up to merger, but anyway, so this will merge first. Then so it merges, then it doesn't collapse to a black hole, so it becomes a massive neutron star. Also, this is massive neutron star, this is massive neutron star, and also this is massive neutron star. And also massive neutron star has an ellipsoidal shape, so not axisymmetric. And so this shows that irrespective of the equation of state, stiffness of equation of state, so massive neutron stars are remnant. So this is an important finding. But it does not arrive forever. So this is this shows the evolution after the merger, and so any long-lived massive neutron star is formed. But after that, angular momentum is transported because it has a ellipsoidal shape, and so angular momentum is transported by hydrodynamically. And then finally it collapses the black hole like this. And so typical black hole spin is about 0.6 to 0.7, so it holds irrespective of the equation of state, and the torus mass is typically about 0.5 solar mass to 0.05 solar mass, 0.1 solar mass. So this is a very typical result which holds so irrespective of the equation of state. So now we consider that so based on the numerical relativity simulation that last 15 minutes of the binary neutron star is like this. So about so in the last 15 minutes, orbital separation become about 700 kilometers for a typical mass of binary neutron star like this. Then it eventually merged due to the emission of gravitational wave. Then as we said, we have two possibilities, but possibility 2 is a case. And so anyway, a massive neutron star is formed. But after its formation, it will collapse to a black hole due to the angular momentum transport. And by the help of the angular momentum transport, usually massive disk is formed around the black hole. And the typical black hole spin is 0.7 or 0.6. It's not very large. And the typical torus mass is 0.05 to 0.1 solar mass or something like that. And this is a typical scenario for a binary neutron star merger found by numerical relativity simulation. Okay, so let me move to the topic on gravitational waves. This is so upper panel shows a typical evolution scenario for binary neutron star merger. If the orbital separation is much larger than the neutron star radius, so each neutron star may be regarded as a point mass. And also the radiation reaction time scale is much longer than the orbital period. So for such phase, post-Newtonian approximation works very, very well. But if the orbital separation becomes, as I say, less than about 5 or 4 neutron star radius, so tidal deformation effect become important. So this means that the point particle approximation break down. For such phase, post-Newtonian approximation together with a tidal coupling or numerical relativity simulation in which we can take into account the finite size effect is important, is necessary. And eventually they merge, so then system is in a dynamical, and general relativity is very important. For such phase, numerical relativity simulation is necessary. And by combining these studies, schematic figure for gravitational wave become like this. So here, post-Newtonian calculation works well. And here, post-Newtonian with the tidal coupling effect, our numerical relativity can describe the waveform. And for the final phase, numerical relativity is necessary. And up to here, the signal is the so-called chirp signal. And here, so you can see that quasi-periodic gravitational waves, which is emitted by the hypermassive neutron star. Because the hypermassive neutron star is rapidly rotating and the shape is not axisymmetric, so ellipsoidal shape. So as a result, high frequency gravitational wave with a high amplitude emitted. Okay, so for this gravitational waveform, so there are two interesting phases related to the equation state study. One is that the rate in spiral phase here. And the other is a major phase. So this is emitted by the massive neutron stars. Here, so typical frequency is about 500 to 1 kilohertz. And here the typical frequency is 2 to 4 kilohertz. So it depends on the equation state. Okay, so I'll describe the detail about the gravitational wave form so separately. And first, I'd like to talk about the rate in spiral gravitational wave form. So at such phase, tidal, as I said, tidal effect play an important role. So if the tidal effect become important, what happens? So this is the answer. So anyway, so this is almost purely Newtonian effect, and this is a Newtonian potential between two stars. So if the, each star is a point particle, we only have this part. But if tidal deformation occurs, these terms appear. This is a purely, almost purely Newtonian term. And according to the post-Newtonian definition, so this is a 5 post-Newtonian term. So this means that it seems to be a very small. But here the coefficient is very large. So here the coefficient is proportional to the total mass, each mass to the each radius fifth. So this means that if so at the major orbital radius become about 2 or 3 stellar radius, so this means that large R over R is not very small at the major. So this means that in the rate phase, so just before the major, this new potential become very important role. And in the final phase, gravitational wave amplitude depends not only on the each mass but also on the tidal parameter. Okay, so let me show you some example of the analytic computation, so which is calculated using the the so-called effective one-body formulation. For this case, each mass is a typical one. And so neutron star has we assume that neutron star has a large radius. So anyway, so in the early phase, so red curve shows that the evolution with the tidal effects, and the green curve shows the evolution with the tidal effects. Tidal with this equation state. Then so you see that in the early phase, so two curves not completely, so almost overlap. But in the close orbit, deviation between two curves appear, and as a result, gravitational wave form, gravitational wave phase also disagree. And in the final major phase, so this is major phase, so a phase difference is very large. So this means that by observing the gravitational waves just before the merger, so we may be able to constrain the equation state. This is the other figure. So this is based on the Taylor-T4 calculation, but results are qualitatively essentially the same. So in this figure, I show that gravitational wave form for the point particle case, and for the tidal deformation cases. But for this, so radius is fairly small. For this case of APR4, radius is 11 kilometer. But for MS1, so radius is 14.5 kilometer. So you can see that depending on the equation state, phase gravitational phase evolution are different. And of course, for smaller mass is for red curves. For smaller mass, result close to the point mass particle case. But anyway, so depending on the radius of a neutron star, evolution of a phase are significantly different. So this is a very interesting possibility. And recently there are a couple of several research in these topics. And about 2 years ago, Chibo Damo and his collaborator analyzed this waveform using effective one-body formulation. And he suggested that for typical mass binary neutron star or less mass binary neutron star, EOS could be constrained by observing by analyzing this type of the gravitational waves. If the signal to noise ratio of the gravitational wave is sufficiently large means that larger than about 16 or something like that. But very recently, UWM group shows that systematic error in the EOB and the gravitational wave template will give a very serious damage. So this means that we have to prepare the very accurate template for this purpose. So the question is that probably EOB is not very bad, but the question is that can EOB provide accurate templates or not? And so in the last a few years, Bernoulli and Hotogezaka and the collaborators showed that EOB will be acceptable for most of inspiral phase, except for the last couple of orbits. But their numerical relativity, they compare their numerical relativity result with effective one-body simulations, and they show that at least up to the last few orbits, EOB is likely to be okay. But their numerical relativity simulations are not very long, and so for this purpose, for comparison, so we need a huge long waveform. And also, initial condition should be very accurate. So very accurate means that initial condition should not have eccentricity. But for in their work, so eccentricity is not neglected. So obviously, more sophisticated study is necessary. And so we also working in this topic. For example, QTOC is now making an effort to reduce eccentricity, and now this is an example of the gravitational wave form with better initial conditions. So in this case, initial eccentricity is 10 to minus 3 or something like that. And also, so I just heard this week that Caltech team and in particular, so Roland is also working with a very long-term and highly accurate simulations. And I think that this type of their study is very important for this area. And probably so, in particular, this study will be will resolve this question. So can you be good or not? Okay, so now I'm talking on the other gravitational waves from massive neutron stars. This is for gravitational wave form. For all mass of each neutron star is 1.3 and 1.4 solar mass, but the equation of state are different for models. And for this case, radius is rather small, and for this case, a little bit larger, and so on and so on. This is radius is very large. And anyway, so qualitatively, gravitational wave is very similar. So inspiral waveform and the major waveform. So major waveform are determined by the massive neutron star is formed. And but the qualitatively is the same, but quantitatively waveforms are different, in particular around here. So for example, frequency of gravitational wave for this case is rather high. High means that more higher than 3 kilohertz. But if the radius is larger, frequency become lower. So in this case, 2 kilohertz. So this suggests that if we can observe the gravitational wave form from the massive neutron stars, we could constrain the equation state. So specifically, if we can determine the frequency of gravitational wave, and here, so this has a very important information about equation state. Okay, this is a Fourier spectrum of the this gravitational wave form. So this Fourier spectrum. So as expected, so we have a Fourier peak because the gravitational waves are quasi-periodic. And this is a case that the red line shows a case. This is a case for a small neutron star radius, and this is a case or large neutron star radius. So we have correlation. And this is a design sensitivity of advanced LIGO, and this is a neutron star optimized sensitivity for advanced LIGO. And for this case, we said that the distance to the source is 50 megaparsec. But anyway, so this shows that even by advanced, so design sensitivity of advanced LIGO, so it will not be very easy to detect a gravitational wave because the signal to noise ratio is at most 3 or something like that. But we have a very sharp peak, so if we could determine this sharp peak, so it will have a very important information about the equation of state. So anyway, so EOS is very strongly reflected in the typical frequency. This is a figure of a peak frequency, so the peak of a Fourier spectrum as a function of the radius of a particular mass. So for this case, we choose that radius of 1.6 solar mass neutron star. So I don't have a reason. So the reason is that Basu and Yanka did a similar study before we did, and because they chose this value, so we chose this value. But anyway, you can see that a very clear correlation. So this plus shows that the Basu-Ein's result, and the others are our result. And you can see that the very good correlation between this radius and the peak frequency. And this suggests that if we could determine the, for example, peak frequency at about 2.9 kilohertz, then so we could constrain the radius of the neutron star within about 1 kilometer or something like that in this area. So of course, it's not easy to determine the peak frequency of gravitational waves, so it has a possibility. Okay, so this is a summary about gravitational waves from the binary neutron star and equation of state. And as I talked, there are two interesting phases for gravitational waves. One is in a rate inspiral phase, and if distance to the source is within about 100 megaparsec, and the rate inspiral gravitational wave form is detected, so they could be used to constrain the equation of state. But as UWM team reported, more accurate template is necessary, and numerical relativity has to do many things in this area. And also, merger phase and subsequent hypermassive neutron star phase has important information about gravitational waves. But for this, so we need a Racky event. So Racky event means that distance should be within about 30 megaparsec or something like that. But it has an interesting possibility. Of course, if ET or advanced detector will be constructed, our situation will be changed, and we will have more chance. Okay, so from now, so I'll talk about the mass ejection and the electromagnetic counterparts. I change top topic. Okay. So anyway, so after the merger of binary neutron star, mass is ejected. So the reason, we have two reasons why the mass is ejected. One reason is that at the merger, strong shock occurs, is generated, and the thermal pressure is highly enhanced. As a result, mass is ejected. This phenomenon is, in a sense, similar to the supernovae, so a prompt explosion of supernovae. And also, we have the other reason that after the merger of binary neutron star, black hole is not formed. So rather, hypermassive neutron star is formed. And also, hypermassive neutron star or massive neutron star has an ellipsoidal figure. As a result, it exerts a torque as a matter surrounding the hypermassive neutron star. So this is also very important for the mass ejection. By these two effects, mass is immediately ejected after the merger. And I should note that other effect, like wind due to the Newton pressure and magnetic pressure could play an important role. But so today, so I only focus on these two dynamical effects, shock heating and non-axisymmetric hypermassive neutron star. Okay, so let me show you an animation of the mass ejection. In this example, so I choose a slightly asymmetric binary neutron star, 1.2, 1.5 solar mass, and the EOS is APR4. So for this case, radius of each neutron star is 11 kilometers. And the left figure shows that fairly so narrow region of the major, and the right panel shows that wider region. So for this case, so length is only 150 kilometers, but for this case, length is more than 1,000 kilometers. Okay, show you. So this is the animation just after the onset of the merger. Okay, so after the onset of merger, shock occurs and also tidal effect ejects the material. So you can see the propagation of the material like this. So we check that this has escape velocity. And fastest speed is 0.7 or 0.8 speed of light, very fast. But in average, speed of the ejecta is about 0.2 speed of light. And for this example, ejecta mass is about 1% of the solar mass. So this is animation in the equatorial plane. Shock heating and the tidal effect play an important role. And in the next slide, I will show the animation in the in a meridian plane. So y equals 0. In this case, y equals 0 plane. So you can see that how shock heating play an important role. Okay, so anyway, so after the merger, shock occurs, then so materials ejected in a vertical direction. So you can see that not only to the equatorial plane, but also to the vertical direction, mass ejection occurs. So, and also it is interesting to see that ejecta shape is almost spherical, quasi-spherical. So this means that not only the tidal effect, but also the shock heating play an important role. So anyway, so we performed many simulations changing the equation of state and the mass ratio and so on and so on. This is, in a sense, a summary of our study for mass ejection. And this shows that ejected mass as a function of the radius of 1.35 solar mass neutron star. So for this case, equation of state is, so neutron star radius is small, and for this case, neutron star radius is large. And this shows that for small neutron star radius around here, typical mass of ejecta is about 1% of a solar mass. And also, it is found that ejecta mass depends only weakly on the mass ratio. But for larger neutron star mass, typical ejecta mass is very small, but typically 0.1% of a solar mass. And in this case, ejecta mass is higher for highly, not highly, so asymmetric binary. So here Q is a mass ratio, and Q equal 1 is equal mass. So red point shows the equal mass result, and triangle shows that unequal mass result. So for this case, for radius of neutron star is fairly large. In this case, mass unequal mass effect is important. So this means that anyway, so for small mass, shock heating is important. So this is due to the small radius of neutron star. And for larger radius, but so shock heating is not very important. So this is an important finding. But anyway, so what is important here is that ejecta mass depends very strongly on the equation of state. This is an important point for the later talk. Okay, so anyway, mass is ejected. Mass is likely to be ejected from the binary neutron stars, and such ejecta could shine. So there are at least two popular scenarios by which ejecta can shine. One is that the so-called kilonova macronova scenario, so which is based on the radioactive power of the ejecta. I will talk this later. And the other is that the so-called afterglow type radio flare. So in this scenario, so ejecta expand, then so sweep the interstellar matter, and eventually a shock occurs, and by the shock heating, so ejecta shine. And for this case, typical duration of the ejecta, so electromagnetic signal is about, for upper case, is about 1 to 10 days. By contrast, for this case, we need a long time to sweep the interstellar matter. So as a result, up to the peak luminosity, so it takes a long time, so year to 10 years. So due to this reason, I focus here only this scenario. So this is more detail about the this radioactive powered scenario. And then so the essence is that ejecta is a neutron rich. So neutron rich. So as a result, it could produce a huge amount of the R process element. So this is a condition for the production of the R process element. So I mean that before neutron capture, so beta decay occur, then so R process nucleosynthesis never occur. But ejecta is dense and also very neutron rich. Then so time scale for neutron capture is much shorter. As a result, nucleosynthesis, R process nucleosynthesis occur. But anyway, so but after the formation of the huge amount of nucleosynthesis matter, so this is a typical trajectory of the evolution of the mass element. So this is a proton number, and this is a neutron number. So anyway, so by capturing the neutron, so mass number increase. But so typically, so neutron is captured. So such element has a large amount of the neutron. Then so it could be unstable and it decay. Then so it radiate electron and so on, so on. But the electron heat up the matter. So then so it shine. This is a basic scenario, which was originally proposed by Lee and Paczynski about 15 years ago. And Lee and Paczynski gave an estimation how to estimate the luminosity and peak duration for this event. And this is their formulation. The M is the total ejecta mass, and B is ejecta velocity, and the kappa is optical depth, opacity, not optical depth, opacity, and F denotes the total fraction of the mass energy, so which contribute to the electromagnetic signal due to the R process unstable element decay. And updating, so originally, so they use completely different value for mass and so on, so on. But updating the latest result, so luminosity and duration become like this. And luminosity is about 10 to 3 times, so about 1,000 times higher than the Eddington luminosity of this system. And typical duration is about 5 days. If the mass is 0.01 solar mass and kappa is 10 centimeters square per gram. So up to 2 years ago, so this is estimated as 0.1 or something like that. But recently, so Dan Keisen and Masami Tanaka show that opacity of the R process element should be much larger, so as 10. Then so luminosity becomes smaller due to the high value of opacity, but duration becomes larger. So anyway, so this is a very good number. 5 days is a good number. Also, 10 to 41 ergs per second is also a good number. So here, so I convert this luminosity to the apparent magnitude at a distance of 200 megaparsec. So 3 times 10 to 41 ergs per second means that about 21.5 apparent magnitude at a distance of 200 megaparsec. This is not a very bad number for the observation. So I will show you later. Okay, so anyway, so now now our understanding of a binary neutron star merger is the following. So we often see some picture of the short gamma ray burst, so in which black hole and torus and the jet are written. But for such scenarios, so we don't have so only for this direction we can observe the binary neutron star merger of electromagnetically. So for example, so for this observer, we cannot observe the binary neutron star merger. But recent theory clarifies that in addition to the such a jet, so we have a ejecta, and ejecta could shine, and so such a electromagnetic signal could be observed from the every direction because the ejecta is almost spherical. So we should write this type of figure, so not this type of figure. We have to write this type of figure for the merger event. And anyway, so this is a very rough estimate, and many people working in the binary neutron star merger are calculating the more quantitatively right curve and peak time. And in this field, I think that Stefan Rosberg is a pioneering person, and he is actively working in this scenario. But he is working in the Newtonian hydrodynamic simulation, and he often uses only one particular equation of state. And we found that the dynamics and the amount of ejecta in Newtonian simulation is highly quantitatively different from those in GR simulation. So we reanalyzed using our numerical data and calculated the right curve of ejecta. So for this, we cannot do anything. So we asked the help of Masaru Tanaka, NOJ. So he performed a radiation transfer study for ejecta and derived the right curves. This is an example calculated by Tanaka. And this is several right curves. So this is the observational magnitude at a distance of 200 megaparsec as a function of time. And upper panel shows the optical band for the right curve. And the red line shows that for the model with ejecta mass is 0.001 solar mass, but with the decrease of ejecta mass, so specifically with the increase of the radius of neutron star, ejecta mass decreased. So anyway, so we show the several lines depending on the ejecta mass. And this shows that for optical band, so peak is reached before 1 day. But for infrared band, so peak is reached at several days. So for example, for this case, peak is reached about 4 days, and for this case, 5 days, and so on and so on. And also, peak luminosity is higher for infrared band. So they show that anyways, for sufficient mass ejection, electromagnetic signal could be observed by, for example, for this case, 4 meter or space telescope. If the event occurs at a distance of 200 megaparsec. And also, they show that the signal is strong in near infrared band. So this is a near infrared band. And this is also originally found by Dan Kaysen. Okay, so it's a time. So finally, so I like to talk about the implications of a short gamma ray burst. This one, so very briefly. So anyway, so they and Kaysen and Tanaka performed this work about 1 year ago. And very fortunately for them, so just after their studies, this GRB occurred. And this is a right curve of the gamma ray burst. So flux as a function of time. And black shows that the gamma ray burst, gamma ray right curve, and the blue shows that the X-ray afterglow curve, and the red shows the optical afterglow curve. And this gamma ray burst occurred at the distance of this one, g equal 0.3506, and the duration is about 200 milliseconds. So it's a typical short gamma ray burst. The fact that's very exciting is that after Tanvir et al. Observed this short gamma ray burst by Hubble telescope, and they observed this gamma ray burst at 9 days after the burst and 30 days after burst at R band. R band is so green, so optical band, and this H band is near infrared band. And this shows that so for visible band, nothing changed at 9 days and at 30 days after the burst. But for near infrared band, so here we have excess. We don't have nothing here, so we have excess. So this 1 point is, and also this is very important. So nothing is very important here. So this 2 point is very important. So Tanvir wrote a Nature paper, and this is their result. And this is a figure, so luminosity, so apparent magnitude as a function of the time since this burst. And the black shows a X-ray light curve. So line shows a model of the afterglow. And blue is also a R band, so optical band luminosity curve. And red dashed line shows a afterglow curve. And this is a point of this one. And this cannot be explained by the afterglow of the gamma ray burst. So this excess should be explained by some mechanism. And so they use the estimate of the Lee and Paczynski, and this solid curve, and inside this curve shows a possible value according to the Lee and Paczynski estimate. And this shows that this access can be explained by the kilonova or macronova scenario. But so this is a very approximate estimation. So we performed the numerical relativity simulation again, and we calculated the light curve of the ejecta. And this is our result. And so we performed the numerical relativity simulation, and Masaru Tanaka performed the radiation transfer simulation for ejecta. And this is apparent magnitude as a function of the time. And we show the two curves for mass with this and with this. And for lower mass, so 0.04 solar mass, luminosity curve becomes something like this. So this error bar, we have error bar. So error bar is due to the uncertainties is the heating of the ejecta. So for strict calculation of the heating rate, so we need to solve the so how the high heavy element is formed, and so on and so on. But it's very complicated, so we skipped this process, and we use a very typical heating rate in this case. But the typical heating rate has an error in the factor of 2. So this is in a sense, error of factor 2 for this heating rate. But for even if with a high heating rate, so this around here, if the total mass of ejecta is small, it's very difficult to explain this observation point. So this means that large radius neutron star is not very good to explain this one. But so if the ejecta mass is fairly large, 0.02 solar mass, and with heating rate is rather high, so in such case, it's possible to explain the this observational point, this one. So this means that if this event occurs a binary neutron-star merger, then so equation of state should be very soft, or small radius neutron star is necessary. Of course, this curve, this point can be explained by, for example, a black hole neutron star binary case. So it's very easy to have a huge ejecta mass for a black hole neutron star binary case. For example, if a mass ratio is 3 to 7 and the neutron star mass is typical, but the spin of black hole, A is the spin of black hole, is very high. So in this case, it's very easy to have a large ejecta mass up to 0.1 solar mass. For such models, so it's very easy to explain this observational point. Very easy. So we cannot say anything about this. So for this, but if we could have some gravitational wave observation, so we may constrain the equation of state. So this is an interesting possibility. Okay, so I'm sorry, I talked longer. So anyway, so this is a summary of this my talk. Gravitational waves from binary neutron star merger is a variable site for exploring equation of state of neutron star. And the efforts, various efforts in numerical relativity are ongoing. And mass ejection in binary neutron star merger is likely to emit strong electromagnetic signal, in particular for equation of state with relatively small neutron star radius. And for such case, it could be a promising electromagnetic counterparts of a gravitational wave. And finally, so I talked that the total mass of ejecta depends strongly on the equation of state. And this means that the luminosity of the ejecta depends very strongly on the equation of state. So this means that by observing the electromagnetic counterparts together with the gravitational wave signal, we will be able to constrain the equation of state. Okay, thank you very much.
Other questions? Oh, don't be shy.
So, when you're talking about, when you're trying to determine what sort of kilonova scenario could be behind GRB's 15603P, so you say that there might be a neutron star black hole, but then since there's a black hole, you can have spin precession, and so so now I'm concerned about if the viewing angle that you have, how that affects how much light from the kilonova you see.
So for the case of black hole neutron star with a precession, so you mean? So, sorry, so I don't understand exactly what you mean. So oh, yeah.
So the fact that you have a black hole means that you have an object that has one of the companions can have an electron spin with some spin precession.
Yeah.
So can you still conclude that the ejecta is somehow in a disk that's co-aligned with the GRB gap? So I'm also thinking about
So probably no one knows. So I think that it depends on how the magnetic field is formed and how the torus surrounding the black hole is formed. So we don't have such consensus. So this is a problem to be solved. So but we don't know right now what happens.
Okay.
Yeah.
The reason that I ask is there's a 2011 paper by Roberts, Kaysen, Lee, and Ramirez-Ruiz
Yeah.
that says that the viewing angle effects can have as large an effect on the
Kilonova.
on the kilonova as the ejection has.
So
So I'm the first to run that paper.
yeah.
Oh.
Yeah.
And so that was mostly though because in the set of simulations we had with small range ejection masses was the difference there. If you eject masses,
Okay.
it might well be the case that the ejecta are somehow always oriented a particular way relative to jet.
Well. Yeah.
Does it matter for how much ejecta you have and how they are distributed in space, whether there's a strong magnetic field and yes, whether there's a strong magnetic field in neutron stars?
So magnetized neutron star. Yeah, so I think that this is a lower limit. In the presence of the magnetic field, magnetic energy, and so neutron wind. So I guess so we are performing a similar simulation, so such a simulation. So our feeling is that this is a lower limit, and in the presence of a magnetic field and neutrinos, total amount of mass increase. So yeah, so maybe it's a good news. So for observation.
So you considered the uncertainty due to our process heating rate when you were looking at whether or not you could match this GRB afterglow excess. But there's also some uncertainty in what the opacities are. How much difference is changing what these lanthanide opacities are by a factor of heating rate?
Yeah, I agree. Yeah. Anyway, so we have a huge uncertainty. Yeah. Maybe so.
So if you put those error bars on that,
Yeah, maybe.
show
Yeah.
Yeah.
You're right. Yeah. Kappa maybe 20 or something like that. Yeah.
So I think we should take further questions out to the wine and cheese reception.
Yeah.
And thank